So let's draw the Lewis symbols for potassium and for chlorine. So what's the element symbol for potassium? K. And how many valence electrons does potassium have? 1. Oh, is that it? That's it. That's all. 1 valence electron. We're done. Okay. Chlorine is the symbol Cl. How many valence electrons does chlorine have? 7. Okay, so we're going to end up with all of them but 1 paired up. If you put the lonely one on the top, the right, the bottom, doesn't matter. But you should have 3 pairs and a single. What if we make an ion? What will potassium do to make an ion? It'll lose an electron. So if it loses an electron, then that goes away, right? Now it has a charge though, doesn't it? So if it's got a charge, we need to indicate the charge. So here we have the electron configuration for potassium. He's going to lose the 4s electron. Now what's the valence shell? It's level 3, and he's got 8. So he lost the outer layer, and we look at this symbol now, this Lewis symbol, and we say, well, he doesn't have 8 electrons. Yeah, he does. We're just not going to go down and draw what's underneath. Now some of the core electrons have become the valence electrons. So he got rid of 1 electron, and now he has 8 valence electrons. And we can see that looking at the electron configuration. Everybody okay with that?
Do we draw them or
We don't throw dots in there. We just understand that if you clear out one level so there's no dots, we understand that there's a full level underneath. For the diagram. We just put the plus sign on there, and we're good to go. So what happened to the electron that potassium lost? Has to go somewhere. It's going to get picked up by the chlorine because the chlorine's looking to gain an electron, right? When the chlorine gains an electron, now 8. And the nice thing about this top, bottom, right, and left, you can look at that just like a pair of like dice, right? You can look at that and you don't have to count. That's why we don't want to do circles, because I don't want to have to count your little dots, right? Top, bottom, right, and left is like looking at the number 6, a dice with the 6 up, and you can just look at it and say, yeah, 8. But this has a charge. If we just put the charge, wrong pen. We just put the charge up here, it can kind of get lost in all the dots. So what we do for anions is we put brackets around the Lewis structure. We put the charge on the outside. And that just helps us okay, this is the Lewis structure, and here's the charge on the outside so it doesn't get lost in the dots. Any questions? Okay. Now this is something you should have encountered in a previous chemistry class. And you may have like repressed it or deleted it from your memory, but hopefully it'll come back to you. So when they do this, when potassium donates or transfers an electron to chlorine, and chlorine becomes an anion, now all of a sudden we've got a positive and a negative, and they're going to be attracted to each other. And that's how ionic bonding is going to happen. So let's use Lewis symbols to predict the formula for the compound that forms between magnesium and nitrogen. Now we've learned how to do that looking at the periodic table, but we're going to do it with Lewis symbols. Okay, and I'm going to try to make some use of color here so that we don't get too confused. So magnesium has which symbol?
Mg.
Mg. And how many valence electrons does magnesium have?
2.
2. So we're going to put 2 dots on magnesium. And nitrogen is N. And nitrogen has how many valence electrons? 5. 1, 2, 3, 4, 5. Okay, so what we're going to do is we're going to try to figure out how could these guys work stuff out together. How could they cooperate so that they can all both get 8 valence electrons? Well, magnesium, the easiest thing for him to do, he's just got 2. He either has to gain 6 or lose 2. Losing 2 is easier. So, it's the best way to show this. So we're going to take that electron from magnesium and give it to the nitrogen. Now this causes there to be some charges involved, right? Now the magnesium has a +1 charge, and the nitrogen is going to have a -1 charge. Is everybody happy yet? No. Okay, so this magnesium wants to get rid of another electron. Well, let's send it up and around this way. So we're going to get rid of that electron, and we're going to put it up there. And this changes the charge on magnesium to 2+. And now what's the charge on the nitrogen? 2-. Have we reached happiness for anybody? Magnesium's happy. Magnesium ditched its valence electrons. Underneath is the full valence shell, so magnesium's good. But nitrogen isn't. So where there's one magnesium atom, there's probably another one, right? So here's another, oops, wrong color. Oops. Too much back and forth. Okay, I think I'm okay now. No. Trying to be too fancy, and it's really backfiring on me. Okay, so here's another magnesium, and this has 2 valence electrons. So it's going to try to get rid of valence electrons also. So this nitrogen is looking for 1 more, isn't it? So the nitrogen says, hey, over here, I'll take one of those for a minute. So the magnesium gets rid of that. And now this nitrogen is -3, and the magnesium is +1. So now we've made this magnesium happy, and we've made the nitrogen happy, but this magnesium isn't happy. Another nitrogen, right? Okay, so let's bring in another nitrogen. So another nitrogen. Five valence electrons. So this magnesium, say, here, take mine. So this goes over there. Now this magnesium has a 2+ charge, and the nitrogen has a -1 charge. Now we've got 2 happy magnesiums, 1 happy nitrogen, and 1 unhappy nitrogen. And we kind of feel like we're just like going in circles, right? My grandma Johnson was, well, she was my grandma. You know, grandmas are kind of funny. We'd have bread at dinner and like jam or honey or something. She'd call it with it, bread and with it. And so she'd take a roll and she'd take some jam, and then she'd eat the roll, but there was some jam left. So she'd need another roll, and so she'd start putting the jam on the roll, but there wasn't enough jam, so she'd take more. She could eat bread and with it all day long, right? She was not skinny. This is what I feel like we're doing here. It's like we're running out of one, we need another, but eventually it'll stop. Okay, so we'll just keep trucking along, eating bread. So we need another magnesium atom. So we kind of see how things are going now, right? So this magnesium will give one electron over here and one electron over there. And now it has a 2+ charge. And there are its electrons that we moved over to the nitrogen. And now the nitrogen has a 3- charge. And finally, we got them all to be happy at the same time.
Do we have to do it that way?
No, you don't. This is for illustration only. Yes?
Isn't nitrogen one of those that'll bond with itself?
It will.
So couldn't it also be the magnesium?
No. Well, the magnesium, why? Because it's asking us for the formula of a compound between magnesium and nitrogen. Now, nitrogen can make itself happy by sharing with another one, and we'll look at that in a minute. And magnesium can be pretty happy as a metal element by itself. But yeah, here we're specifically asked for how do they get together. So then looking at this, what is the formula for magnesium and nitrogen? Well, you count them up. How many magnesiums did we use? 3. Mg, that's not a very good M. Mg, 3. And how many nitrogens? 2. So there is the formula. I did all of that just to show you how we can think about it using Lewis dots and looking at the electrons. Okay, we learned earlier to say, well, magnesium's +2 because of its position in the periodic table. Well, now that we know a little about quantum mechanics and orbitals, we understand that the reason it forms a +2 ion is it wants to get a full valence shell. It wants to lose the 2 valence electrons. That's how it becomes a +2 ion. And nitrogen we learned to predict from the periodic table, it's -3, and then we learned to do the crisscross thing and predict the formula. But it forms a -3 ion because it has 5 valence electrons, and by gaining 3 electrons, it gets an octet. You see that? And no, you do not have to do this every time you make the formula for an ionic compound. That would be ridiculous. You should be able to do it if asked, though. And this is one of the more complicated ones. Something like the first one, potassium and chlorine, that was easy. It's just transfer an electron and be done with it. Any questions? So now we get to the rest of the story. If we look at, in the book it mentions sodium and chlorine, there is energy required to ionize sodium, the ionization energy. And if we look at the electron affinity of chlorine is positive, meaning there's energy gained by the atom by doing that, so that's a good thing. But it doesn't add up to being energetically favorable for sodium to give an atom. It doesn't end up being energetically favorable for sodium to give an electron to chlorine and form an ionic compound that way. So there's a piece missing, and the piece that's missing, which I think someone was asking about yesterday, is lattice energy. So ionization energies, electron affinities cannot explain why ionic compounds form and why this is usually quite exothermic, sometimes violently so. Gives off a great deal of energy. And it has to do with the lattice energy. Lattice energy is the energy associated with the formation of a crystalline lattice of alternating cations and anions. So energy is released when we get these positives and negatives all lined up. And I think a little of, hopefully you've at least seen that toy, magnetics, with the balls and the sticks, and they're magnetic and they just click together, right? It wants to stay together because of the forces of attraction. And I visualize ionic compounds a little bit like that. You've got the cations and the anions, and they stick together because of the attraction between the positive and negative charges. Well, the potential energy is lowered when you get those opposite charges together. And so energy is released as heat, and it's an exothermic process. When we measure lattice energy, it's measured from ions in the gas state coming together. So just the energy of the lattice. So if you have gaseous ions of sodium and chlorine and they come together to form solid sodium chloride, the amount of energy released is the lattice energy. So when these ions coalesce, heat is emitted. They're coming together. Well, that's hard to measure. And so the easiest way to calculate a lattice energy is the Born-Haber cycle. And this is just a theoretical series of steps representing the formation of ionic compounds from their constituent elements. And this is the same idea as Hess's law. So we're taking individual steps which are not actually happening, but we're taking steps that we know the energy for and adding them together so that we can find this missing piece. So we're going to use steps where the change in enthalpy is known, and that the overall change in enthalpy for the whole reaction is also known. It's important to this point here is important, especially since I tend to talk about things, personify them a lot. Formation of ionic compounds is not exothermic because the metal wants to lose an electron and the nonmetal wants to gain an electron. Okay, that helps us to remember what's going on. It's a nice way to think about it, but that's not the real reason. The metal ion, the cation, does not just go around throwing electrons off. You have to buy them from him. Okay? Some of the anions will pay you for an electron, and some of them won't. But overall, the reason it happens is because of the heat that's released in the formation of this lattice. Is when these two things come together, there's this big bonus in energy. So it's like this, really great Groupon deal or something. If these things that you wouldn't necessarily do all come together, you save all this money, right? So there's a large amount of heat released when the cation and anion coalesce to form a lattice. So important to remember, it's not about the metal losing an electron, the nonmetal gaining an electron in terms of energy. It's about when they come together, it's very exothermic when they get together. So this is the Born-Haber cycle for production of sodium chloride from sodium, metal, and chlorine gas. So we can measure, let's see, where are we? I have to orientate myself. Okay, so here is the heat of formation for sodium chloride, the standard heat of formation. Sodium in its standard state as a solid, chlorine in its standard state as a diatomic molecular gas. And so sodium plus 1/2 of a molecule of chlorine combine to form sodium chloride. And we can look that up in a table. We can also look up forming sodium gas from sodium solid, the difference from the standard state to this state. And we can look up the formation, the energy in the formation of chlorine atoms from the chlorine molecule to go to the atoms. And then we can use ionization. The ionization energy for sodium is removing that and forming an ion here. And then the electron affinity of chlorine, there will be some energy given back. So if you look at just these two steps, these guys are higher in energy than what they started from. And so that's not going to cause it to go and be exothermic. But the big deal here is this last purple step. And this is where we get the ions coming together. This is the lattice energy. You can't measure that directly. But you can measure all these other steps. And so we can find the total of this side, and that has to equal this piece that we can measure plus that piece. And so then we can solve for the lattice energy. Any questions? There are trends in lattice energies. And again, they're trends, they're not absolutes. The lattice energy for alkali metal chlorides decreases as we move down the column. So here we're looking at the alkali metals, lithium, sodium, potassium, and cesium. We skipped rubidium, it's okay. The lattice energies get smaller as we go down. Well, what's up with that? And here's a more picture illustration of this. Well, it has to do with the size of the ions. Lattice energy is going to depend on how close the ions in the lattice are. We learned that as we go down a group, that the ions or the atoms get larger, right? So cesium ion is larger than lithium ion. Well, because it's larger, the distance between these two is going to be greater. We're going nucleus to nucleus. Coulomb's law says that the energy is proportional to 1 over r. If the radius, the bond radius, the distance between them is larger, the energy will be smaller. And so the lattice energy decreases here because the ions are getting larger and they just can't get as close to each other. You know, if you're snuggling up with your sweetie, you know, you get really close, right? Well, if you both put on those inflatable sumo suits, can you even get close enough to kiss? Probably not, right? There's this stuff between you, okay? So cesium's wearing a sumo suit and lithium isn't. There's also an effect of ionic charge. So if we compare sodium fluoride and calcium oxide, these were chosen because the distance between the ions is going to be pretty similar. 231 picometers here and 239 picometers. Not a significant difference. But what is different is that calcium is 2 plus, oxygen is 2 minus. The charge on this one is double of the charge on these guys. And so we see the lattice energy of the one with the higher charge is greater. Because Coulomb's law also tells us that the energy is proportional to the product of the charges. So here Q1 is 2 and Q2 is 2. Here Q1 is 1 and Q2 is 1. And so we've got the product being 1 or 4. And if you look at that, 910, what's 910 times 4? 910 times, oh my goodness, calculator. 910 times 4. 3,640. Is that pretty close to 3,414? Pretty close. The attraction depends on the distance between the objects and their charges, the product of their charges. Any questions?
Are we going to need to calculate this?
Are we going to need to calculate this? It's possible. It's possible. This is a very simple form of Coulomb's law, just giving it as a proportionality. And if you know this, then you can think about the rest of it. If Q's are larger, the energy's larger. If the radius, the distance between them, is bigger, the energy's lower. These things can be calculated. It's not super useful, but they can be calculated. So lattice energies are going to become less exothermic with increasing ionic radius. They're going to become more exothermic with increasing magnitude of ionic charge. So what you definitely need to be able to do is something like this. Arrange the following in order of increasing magnitude of lattice energy: lithium bromide, potassium iodide, and calcium oxide. Well, how do we do this without any other information? Well, let's compare two at a time. It's hard to compare three things. So let's look at lithium bromide and potassium iodide. What are the charges on those ions? +1 and -1. Both the cations are +1, both the anions are -1. So charge doesn't come into this. It must have something to do with ionic radius, ionic size. So which is, oh, pointing the wrong place. Which is bigger, lithium ion or potassium ion?
Potassium.
So potassium ion is bigger. We'll put a plus, and this is small. And if we compare bromine and iodine, which one's bigger? Iodine's bigger. And bromine is smaller in size. Okay, so the charges are the same, but the sizes of the ions are different. Which of these do we expect to have a greater attraction, a larger lattice energy? The lithium bromide. These guys can get closer. Okay, so we're supposed to do increasing magnitude of lattice energy. Okay, we'll do this up here by the example. So lithium bromide has greater lattice energy than potassium iodide. So now we have to look at calcium oxide. Well, calcium oxide, each of those has charges of 2. We've got +2 and -2, right? So then we have to look and see, well, how do these things compare in size to the other ones? Calcium is most similar to lithium or to potassium? It's similar. It should be similar to potassium because it's right next to it on the periodic table. It's going to be a little smaller, but not as small as lithium. So this is similar, similar to potassium. And oxygen, we had bromine and we had iodine. Well, how does oxygen compare to those two? It's smaller than both. Okay, so this guy's small, really small. So the calcium is comparable to the potassium. The oxygen is smaller than both of these, probably significantly, because it's 2 rows above bromine. Does this matter? That matters a great deal. So this is similar to that one. This is smaller than both of these, and we have this factored in is this going to have a larger or smaller lattice energy than potassium iodide? It's going to be larger than potassium iodide for sure. How about for lithium bromide?
Larger?
Probably larger. The charge is big because this is Q1, Q2 equals 1. On calcium oxide, Q1, Q2 equals 4. That's going to figure in a factor of 4. And the size difference on the other ions is kind of a wash, probably. Any questions? Yes?
Q2 and Q1. Q2 about 4.
It's 2 times 2. Ah.
Charges don't play.
Well, it would be negative, but it's always going to be negative because otherwise they would repel each other. Any questions? I personally think this particular example is a little too difficult for an exam because we've got some offsetting things here. I would prefer, if we were going to do this, I would prefer to see like calcium bromide or calcium selenide or something where you could better compare this with similar sized but different charges. I don't like having you have to offset size and charge at the same time. I think you should just have to compare one or the other. Yes?
So if it was, if we were looking at a compound that had that had like 2 of one of the species in the binary ionic compound, then
Like
would it be
K2O or something?
yeah, would the total charge still be 4?
I think if we were doing that, we'd still, Q1 is 1 for the potassium and Q2 is 2 for the oxygen, so it would be 2. And you really can't compare this one to that one because this is not a 1-to-1, this is a 2-to-1, and that's a 1-to-1. If you're going to do this, you have to compare with other 2-to-1s. We're trying to stay on the surface, and it gets the water gets muddy really fast, and there's quicksand at the bottom. So let's try to float on the surface here. Any other questions? So comparing our bonding models in reality. Always a good test. Does this bonding model explain properties of ionic compounds? Well, here's some properties. Ionic compounds have high melting points. Does this explain why? Well, the force of attraction between positive and negative charges is very, very strong. In order to melt this, you have to put in enough energy so that the kinetic energy of these ions rises enough that they can break loose from each other and become a liquid. So yes, this does explain the high melting point of ionic solids. These ionic bonds are very strong. Does it explain the non-conductivity of ionic solids? Solid sodium chloride does not conduct electricity. It doesn't. In order for conductivity, we have to have charged things that are able to move. Can the ions in this solid move? No. Are there any free electrons that can be moving around? No. If we take this and dissolve it in water, though, and make a liquid solution, now the ions can move independently of each other, and it will conduct electricity. So this model does explain these observations that we have about ionic compounds. Ionic compounds do have high melting points, but it is possible to melt them, and if you melt them, they will also conduct electricity.